In part 1 of this lecture, we derived the rate expression for the Langmuir-Hinshelwood mechanism. The Langmuir-Hinshelwood mechanism involves reaction between two adsorbed molecules at the catalyst surface. We've broken down an overall reaction into its elementary steps. So for a bimolecular reaction between reactants A and B to form product AB, taking place in a two-phase reactor, we can write 4 steps for the catalytic reaction process. So note that we are not considering any mass transfer effects in this lecture. So we can write the adsorption of the reactant A. We also have the adsorption of reactant B. And then the reaction between the two adsorbed species. And finally, the desorption of the adsorbed products. The Langmuir-Hinshelwood mechanism requires that the surface reaction is the rate limiting step. Therefore, the overall rate is equal to the rate of the surface reaction. So we can write the rate expression in terms of the surface concentrations of the adsorbed species. So the overall rate, negative RA, that is equal to the rate of the surface reaction, R subscript R. Okay, and then we can write this. If the forward reaction rate constant is KFR and the backward step rate constant is KBR, then we can write this as the rate of the forward step, so that's KFR, times the surface concentration of A times the surface concentration of B, minus the rate of the backward step, which is KBR, so rate constant, times the surface concentration of AB, times the concentration of the free sites, CS. The adsorption and desorption steps are all in equilibrium. Okay, so we can use them to write an expression for the surface concentrations in terms of the bulk concentrations, which we can then substitute into the rate expression. Okay? In order to eliminate the surface concentrations and express this overall rate in terms of the bulk concentrations. Today, I will teach you a shorter way of deriving the rate expression without having to go back to the first principles. We just need to know, number 1, what the rate limiting step is. In most cases, it is the surface reaction step. And then number 2, that the adsorption and desorption steps are in equilibrium. Therefore, we can use the Langmuir isotherm to express the surface concentrations as a function of bulk concentrations. So if you can remember, if only one component is adsorbed, then our Langmuir isotherm is in this form. So the surface coverage of A, or the concentration of the adsorbed A, or the surface concentration of A, over the total number of sites, this is equal to the adsorption equilibrium constant for A times the partial pressure of A, 1 plus kPa, PA. Okay, so the subscript P in the adsorption constant indicates that we are expressing the bulk concentrations in terms of the partial pressure. Okay, so we can generalize this. Okay, so say we have more than one components that are being adsorbed. So they are competing for the active sites. So this is the Langmuir isotherm for one component. But the more general form of this equation, okay, so is for the competitive Langmuir adsorption, okay, or the competitive Langmuir isotherm can be written as, okay, so say you have different species competing for the active sites. So for a component I, we can write the surface coverage as, okay, the surface concentration of component I. Okay, so this is equal to the adsorption constant for component I times the partial pressure of component I divided by 1 plus the summation of the product of the adsorption constant and the partial pressure of the component or the components that are competing for the active sites. Okay, so this summation is over all of the species or components that are competing for the active site. So for example, so in this reaction, we have AB and the product AB competing for the active sites. Okay, so this summation is all over J, and J is an index for the set containing all species that are competing for the active sites. And then I can write this equation for each I. Okay, so I, the component I, or the index I, represents a component that is involved in the reaction. Okay, so this equation is for all I in the element of the set containing the species involved in the reaction. So in our reaction, okay, so the species are AB and AB. Okay, so if you can see here, if you only have one component being adsorbed, this will simplify to your one component Langmuir isotherm. Okay, so this is more general. And then from the site balance, so again, the site balance, so CT. So for our example, this is equal to the free site plus the surface concentration of all species that are adsorbed. So that's CAS plus CBS plus CABS. Okay, so if you substitute, so if you evaluate this for each of the components and you substitute the concentration of the adsorbed species here, then you can solve for CS, and CS over CT will be equal to 1, okay, all over 1 plus the summation KPJ, okay, all over J, which are all of the species that are competing for the active sites. Okay, so these are the two equations that we need. Okay, so concentration of the free sites and the surface concentrations of all of the components that are adsorbed. Okay, so you'll just have to remember these two equations. But they are easy to remember. Yeah, so they have the same denominator. And the numerator for this one is KPI, PI, and this one is 1. So now, let's apply the competitive Langmuir isotherm formula to the problem in your homework. So you are given the following overall reaction. So you have A plus B goes to product AB. And this is taking place in the gas phase. You are asked to derive the Langmuir-Hinshelwood rate expression in terms of the partial pressures. So let's write the elementary steps involved in the reaction. So we have the adsorption of A. We have the adsorption of B. And then the surface reaction between the two adsorbed species. And then we have the desorption of the products. The Langmuir-Hinshelwood mechanism requires that the surface reaction, so this step, is the rate limiting step. Therefore, I can write my overall rate as negative RA equal to the rate of the surface reaction step. And if I denote my forward reaction rate constant as KFR and the backward reaction rate constant as KBR, then I can write this as, okay, so the rate of the forward step, so that's KFR times the concentration, surface concentration of A times the surface concentration of B minus the rate of the backward step. Okay, so that's KBR times the surface concentration of the product, CABS, times the concentration of the free sites, CS. So this is my rate expression. But I would like to replace the surface concentrations by the bulk concentrations. So I can use my competitive Langmuir isotherm formula to do that. So I can use that to relate the surface concentrations to the bulk concentrations. Okay, so to do that, let us identify the components or species that are adsorbed or that are competing for the active sites. Okay, so I'll write here adsorbed species. Okay, so the components that are competing for the active sites are A, B, and the product AB. Okay, so you can also write this as AS, BS, or ABS, but I'll just write it this way. So this is just to indicate which species are competing for the active site, so it's easy to apply the competitive Langmuir isotherm formula. Okay, so here are the formula again. So we have the surface concentrations of component I. And this is the concentration of the free sites. Okay, so if I is equal to A, then this will become CAS over CT equal to KPAPA. And then the denominator is 1 plus the summation of the product between the adsorption equilibrium constants and partial pressure of all of the components. Okay, so let's do that for A. So applying the formula, so we can write the surface concentration of A, CAS, over CT. Okay, so using the competitive Langmuir isotherm formula, so this is K PA times the partial pressure of A divided by the denominator, D. Okay, so the denominator again is just equal to 1 plus, okay, so adsorption equilibrium constants times the partial pressure for all of the species that are competing. Okay, so let's do it for A. So K, PA, PA. And then for B, KP, B, PB. And then for AB. So we have K, P, AB, P, AB. Okay? And then I can also write the surface concentration of B divided by CT. So that's just equal to K, PB, PB all over the denominator. And similarly for CABS over CT, so that's just equal to KP, AB, PAB all over D. Okay? And then we have a CS here, so we need to write that as well. And the formula is here. Okay? So CS over CT is just 1 all over the denominator. Okay, so I'll write that down. So CS over CT is equal to 1 all over the denominator. Okay, so now I can use these expressions to eliminate the CAS here and replace them with the bulk composition. So in this case, we're using partial pressures. Okay, so let's do that. So negative RA, this is equal to KFR. But this time, I will write my CAS using this. Okay, so we have KPA, PA times CT, okay, all over D. Okay, so this term here is from here. Okay, so that's CAS. Let's do the same thing for CBS. So CBS is KPB, PB, CT, all over D. Okay, minus KBR times CABS. So I'll get CABS here. So we have KP, AB, PAB, have CT, and D, and then CS. CS is just CT over D. Okay? So now I just have to manipulate this algebraic equation. So we need to write this in a more meaningful form so we can gain insights from it. So let's rearrange this so that it will show the kinetic term, the driving force term, and the adsorption term. Okay, so firstly, I can take the CT square out, and then I'll put them in the same denominator as well. So we have D squared. Okay, so I'll write this as CT squared, D squared, and we will have KFR, KPA, PA, KPB, PB, minus KBR, KPAB, PAB. Okay? And then I can factor out the rate constant for the forward reaction, KFR, as well as the adsorption equilibrium constants for A and B. So let's do that. So we can write this as KFR, CT squared, KPA, KPB, all over D squared. Okay? So what are the terms that are left inside the bracket? So we have PA, PB, minus, okay, so I have KBR, but I have also factored out KFR, so this should appear in the denominator of this term. And so are the KPA and KPB terms. Okay, and then let's bring down the remaining terms. So I have KPA, KPAB, and PAB. Okay, so can you see the form now? It's starting to emerge. Okay, so let's look at our steps again and define the equilibrium constants for each step. Okay, so I will write it here. Okay, so adsorption equilibrium constant for A. So that's KPA. So we can write that in as the concentration of AS divided by the concentration of A, but this time we are using the partial pressure to represent composition. So this is PA times CS. Okay? And then let's write the adsorption equilibrium constant for B. So looking at this adsorption reaction, so KPB is equal to CBS divided by PB times CS. Okay, and then KR, this is equal to CABS times CS divided by CAS times CBS. Okay, and then the desorption constant is, so again, this is partial pressure. This is our product in the bulk phase. So that's PAB times CS divided by CABS. Okay, and then we have that special property for the equilibrium constants. So, okay, so we know that the product of all of the individual equilibrium constants for each of the steps. So KPA times KPB. Okay, so KR times KD. Okay, so KPA, KPB, KR times KD. So these are just the product of the individual equilibrium constants for each of the steps. Yeah, so the equilibrium constants for this is KPA. This one, the adsorption equilibrium constant for B is KPB. For this step, this is KR. And for this one, this is KD. Okay? So we know that if we multiply them, this will just give us the overall equilibrium constant for the overall reaction. Okay. Okay? So this is equal to the overall equilibrium constant, K. Okay? So this is because when you sum up the left-hand side of the equations and the right-hand side of the equation, it will give you the overall reaction. Okay, so the product of the equilibrium constants is just equal to the overall equilibrium constant. But you can, if you want to convince yourself, you can substitute the definitions to each of the terms here. So let's do that. Okay, so I'll write here as well. So what is the definition of the overall equilibrium constant? So that's capital K. So I need to look at my overall reaction. Okay, so overall equilibrium constant, this is in terms of the partial pressure. These are bulk concentrations. We need the bulk concentrations or bulk composition. So product, partial pressure of AB, this is equal to partial pressure of A times the partial pressure of B. Okay, so let's check that this is indeed the case. Okay, so KPA is CAS. Okay, so from here, CAS, PA, CS, and then KPB is this CBS, PB, CS. Okay, so KR is this CABS, CS, CAS, CBS. KD is P, AB, CS, CABS. Okay, so let's cancel out some terms. So the surface concentrations will cancel out. So CAS, cancel out with this one, CBS with this one, CABS, and then the CS. Okay, so we have two CS here. I can cancel this out. So this will become PAB. This is PA over PB. Okay, but K is equal to this, PAB, PA over PB. Okay, so therefore we have proven this. Okay, so that is true. Okay, but we know as well that KR, okay, so equilibrium constant of the surface reaction, this is just equal to the ratio of the forward rate constant and the backward rate constant. So we have KFR, KBR, okay, and also KD. We can write this as 1 over KB. Okay, so this is the adsorption equilibrium constant for our product, AB. And this is just the inverse of the desorption constant. Okay, so as you can see here, this term here, okay, this is 1 over KR. Okay, so using this definition here. And then using this KD 1 over KAB, okay, so we can write K as KPA, KPB, KR. Okay, so KD is 1 over KAB. So this one is K. Okay, so I should have a P here. Okay, so KPAB. Okay, so K is equal to this. Okay, and then going back here, so you can see here KPAB, and then you'll have KR here, KPA, KPAB. So I'll write this, hold that here. So okay, so the constants. Okay, so that lot here is equal to KPAB all over KFR, KR, because of this. Yeah, KBR over KFR is just KR, and then I'll have KPA, KPB. Okay, so if you compare this with this, okay, so you'll see that this is just equal to, so this whole dot here, this is just equal to 1 all over the equilibrium constant. Okay, so now we're ready to write our rate expression. Okay, so let's write that here. So we have negative RA. This is equal to this. KFR CT squared KPA KPB, okay, multiplied by PA PB, okay, and then this whole bunch of constants here is just actually equal to 1 over K, okay, 1 over the overall equilibrium constants. So that's PAB all over K, okay, so overall equilibrium constants. And don't forget your denominator squared, okay? So denominator squared, okay, denominator is this. So we have denominator squared here. Okay, so d squared, so we have 1 plus kPa PA plus kPb PB plus kPab PAB squared. Okay, so this is the form that we want. So this is our kinetic term. This is our driving force term. Okay, and the denominator, this is our adsorption term. This is the rate expression that we just derived. Note that in my solution, I used K instead of K prime to simplify the notation. But in my derivation, I also defined K as PAB over PA times PB. So what is important is in your solution, you define what you mean by K prime or K. This term, okay, so this one is the driving force term, and this tells us how close the system is to equilibrium. This term, on the other hand, which we saw on the denominator of our rate expression, is the adsorption term. What does this tell us? The adsorption term describes the retarding effects of the adsorbed reactants and products. So the more species are adsorbed on the active sites, fewer sites will be available for the reactants to adsorb onto. So you will see a reduction in the overall reaction rate as this term increases, which makes sense because this term is in the denominator. Now, we've put everything in terms of measurable quantities, except for one thing. Do you know which one? The total number of sites is not something that can easily be measured, but we do know that it must stay constant if we don't consider catalyst deactivation. Since all of the other kinetic parameters are also constant, we can lump everything into a single constant K. So we arrived at our final expression. It is worth noting that the numerator of this expression follows the form of the rate expression that you've seen in your homogeneous reaction engineering. The new element here is the denominator. This shows that the rate of a heterogeneous catalytic reaction also depends on the amount of chemically adsorbed species on the catalyst surface, which is represented by the adsorption equilibrium constant in this term. This is the most general form of the Langmuir-Hinshelwood kinetics, but you can also make simplifying assumptions such as irreversible reaction or weakly adsorbed species. For irreversible reaction, the overall equilibrium constant is very large. Remember, the overall equilibrium constant is the ratio between the forward and the backward rate constants. So for irreversible reaction, we can neglect this term, and we can simplify our rate expression to this. Another assumption we can make is that the product is weakly adsorbed. That means that the adsorption equilibrium constant for the product AB, that's KPAB, is very small, so we can neglect this term. This is the resulting rate expression if the product AB is weakly adsorbed. For our next activity, I would like you to consider the reaction in the activity L2.1, which is the oxidation of carbon monoxide. I would like you to develop an expression for the initial overall rate of reaction. The key word here is initial. What simplifying assumptions can you make at the start of the reaction? Pause the video now. What answer did you get? You can just use the expression that we derived earlier and substitute CO, carbon monoxide for A, O2, oxygen for B, and carbon dioxide, CO2 for AB. At the start of the reaction, there is hardly any product formed. So the product concentration or partial pressure is much smaller than the reactants. So we can neglect the terms with PCO2 or partial pressure of CO2. So this one and this one. So this will be our rate expression. The Langmuir-Hinshelwood mechanism has this characteristic shape when you plot the rate of reaction versus the partial pressure of A. It increases at the start and reaches a maximum and then falls off slowly towards zero. Note that the rates and partial pressures are quantities that are measurable in the lab. So you may be given this data, or you can obtain them yourselves through experimentation and find out what the mechanism is taking place in your catalytic reactor. The qualitative reasons for this shape are that with partial pressure of A or PA equal to zero, there are no molecules of A adsorbed, so the reaction rate is zero. As the partial pressure of A increases, the amount of A adsorbed increases, thus increasing the rate. At some point, A and B are adsorbed in equal quantities, and this gives the maximum rate. When the partial pressure of A increases further, in other words, you increase the composition of reactant A in the bulk phase further, more A will get adsorbed, and the additional A adsorbed competes with B for sites and dominates. Thus, the amount of B that can be adsorbed reduces, and because the rate also depends on the concentration of B adsorbed, the rate reduces. If you increase the partial pressure of A further, in the end, A can completely dominate, and there will be very little B adsorbed, causing the rate to fall to zero again. We can see that this behavior is consistent with the rate law. The square of the adsorption term in the denominator gives the curve or gives the plot of RA versus PA, a turning point or a maximum. This behavior of the Langmuir-Hinshelwood mechanism has been observed in real experiments, such as for the oxidation of CO, or carbon monoxide, we considered in our activities in this lecture. Here you can see that the rate increases at low carbon monoxide partial pressure, and then it reaches a maximum and then decreases. The rate decreases because from this point on, CO, or carbon monoxide, is taking up most of the active sites, and very few sites are available for oxygen to adsorb onto. There is a different type of Langmuir-Hinshelwood mechanism, one where the different species adsorbed onto different active sites. Before, we assumed all active sites are the same. In what we call a dual site model, A and B adsorbed in different types of active sites. So for example, A can only get adsorbed on site S, while B can only get adsorbed on site S star. In this case, we need to define different site balances for each type of site. So one for site S and one for site S star. Knowing the different sites the different species adsorbed onto, we can derive the adsorption isotherm for each species using the competitive Langmuir isotherm formula. Let's derive the rate expression for the dual site mechanism. As before, let us consider the overall reaction between A and B to form AB. So here, A gets adsorbed on site S to form AS. And B gets adsorbed on site S star to form BS star. And then we have the surface reaction between the two adsorbed species, AS star plus BS star. Okay, so here we will assume that the product AB only gets adsorbed on site S, or it will stay on site S, freeing up site S star when AS and BS star reacts. And in this case, we will only consider the forward step. Okay, so we will assume that the surface reaction is irreversible. Okay, because I would like you to do the reversible one as your homework. Okay, so here AS plus BS star, it will give us ABS plus S star. Okay, and then finally, we have the desorption of product. So we have ABS, okay, going to AB plus S. So the Langmuir-Hinshelwood mechanism requires that the rate limiting step is the surface reaction step. Therefore, we can write our overall rate as equal to the rate of the surface reaction. Okay? And we can write this as follows. So denoting the rate constant for the surface reaction as KFR. So we can write this as KFR times CAS, okay, times CBS star. So this is our overall rate expression, but we need to replace the surface concentrations, CAS and CBS star, with the bulk concentrations, PA and PB. So we can do that by using the competitive Langmuir isotherm formula. Okay? So in order to apply that, we need to identify which species get adsorbed on different active sites. So on site S, we know that A and the product AB get adsorbed. And for S star, only reactant B. Okay, so to remind you, here are the formula again for competitive Langmuir isotherm. Okay, so let's write it for component A. So for component A, so here I would like an expression for CAS. Okay, so CAS over CT. So CT is the total number of site S. Okay, so this is equal to, using the competitive Langmuir isotherm formula. So this is for A, so we have K PA PA divided by 1. And then the rest of the term here will represent contribution from all of the species that are adsorbed on that site. Okay, so in this case, we have A and AB. So we'll see terms here for A and AB. So KPA, PA plus KPB, PB. Okay, and then we need an expression for CBS star. So for CBS star, okay, so using the competitive Langmuir isotherm formula, this is CBS star over CT star. Okay, so CT star, that's the total number of site S star. Okay, so we write K PB PB divided by, so on S star, only B gets adsorbed. So in denominator, we only have contribution from B. Okay, so we write 1 plus KPB PB. Okay, so now we have an expression for CAS and CBS star in terms of the partial pressures PA and PB. So we can just substitute them into this rate expression. So let's do that. So we'll have negative RA is equal to KFR times CAS. CAS is given by this, so I'll write K PA PA times CT divided by 1 plus K PA PA plus K PB PB. Okay, and then we have CBS star there. So I'll use this. So we'll have KPB PB CT star, okay, divided by 1 plus KPB PB. Okay, and then let's tidy up a little bit. Okay, so overall rate is equal to KFR. So you have CT star. Okay, my adsorption equilibrium constants KPA, KPB. And I have my partial pressures PA, PB. Okay, and for the denominator, I have 1 plus KPA, PA plus KPB, PB. 1 plus KPB, PB. This is the rate expression that we just derived for the dual site mechanism. Finally, we have the Elly-Rideal mechanism, where only one species adsorbs, and then the adsorbed species reacts with another molecule in the fluid phase. The product is initially adsorbed and then desorbed, as in the Langmuir-Hinshelwood mechanism. To derive the rate expression for Elly-Rideal mechanism, we just need to go through the same steps as before, defining the surface reaction rate as the rate limiting step, and then defining the isotherms and substituting for the surface concentrations, and getting the results in terms of only bulk concentrations and equilibrium constants. Let's derive the rate expression for the Elly-Rideal mechanism. So let's consider the overall reaction, A plus B. So let's consider C as our product this time. So in Elly-Rideal, only one of the reactants is adsorbed. So let's take that as A. So we have A plus S goes to AS. Reactant B stays in the fluid phase, and the reaction takes place when B in the fluid phase collides with the adsorbed species. So we have AS plus B. Okay, it forms CS. Okay, so the product C is adsorbed on the site S. So it needs to desorb and go back to the bulk phase. So we have CS, C plus S. Okay, so in Elly-Rideal, the rate limiting step is also the surface reaction step. So therefore, we can write our overall rate, negative RA, as equal to the rate of the surface reaction. And if we denote the forward and backward rate constants as KFR and KBR, then I can write this rate as KFR times CAS, okay, times, so this time I'll use PB, partial pressure B because B is in the bulk phase. Okay, so minus the rate of the backward step, so that's KBR, CS. Okay, so this is our overall rate, but we need to replace the surface concentrations with the bulk concentrations. So we can use our competitive Langmuir isotherm formula. So what are the species that are adsorbed on site S, on the A, and C? Okay, so let's write the expression for the concentration of AS. So surface concentration of A, CAS, over CT. Okay, so using the Langmuir, competitive Langmuir isotherm formula. So this is K, PA, PA. Okay, and then 1 plus, okay, so contributions from the species that are adsorbed. So I have contribution from A and from C. And then for surface concentration of C, so we have CCS all over CT. Okay, so this is equal to K, PC, PC. Okay, again, 1 plus. Okay, so it's the same as this one. KPA, PA, and KPC, PC. Okay, so now I can use these expressions to replace CAS and CCS in the rate expression. So let's do that. So negative RA is equal to KFR. So CAS, that's KPA, PA, CT. Okay, so 1 plus KPA, PA, plus KPC, PC. Okay, and we have PB there, so don't forget PB, minus KBR and CCS. CCS is equal to this one. Okay, so we have KPC, PC, CT all over 1 plus KPA, PA plus KPC, PC. Okay, so now we would like to write this in a more meaningful form, showing the kinetic term, the driving force term, and the adsorption term. Okay, so let's factor out KFR. I'll also take KPA outside the bracket, and I have CT in each term on the right hand side. So I'll write CT here, and they have the same denominator. Okay, so what are the terms that are left in the brackets? So for the first one, I have PA, PB. Okay, so this is minus. Okay, so here I have K, BR. Okay, so I have KPC and PC. But okay, so I have factored out KFR and KPA, so they should appear in the denominator here. KFR, KPA. Okay, and the denominator is here. This is here. So I know that this is equal to 1 over KR. Okay, and from our elementary steps, okay, we know that the overall equilibrium constant K will have this property. So if we denote the overall equilibrium constant of this reaction as K prime, okay, so I'm using prime this time. And for the adsorption step, this is KPA, and this is KR for the surface reaction. And for the desorption, this is KD. And we know that this is equal to 1 over K, P, C. Okay, so the desorption equilibrium constant is the inverse of the adsorption equilibrium constant. So we know that the product of the individual equilibrium constants is equal to the equilibrium, the overall equilibrium constant. So we have K is equal to K, PA, KR, KD. Okay, so to check that, if you want to convince yourself, so I'll write this out. So this is KPA is CAS all over PA CS. Okay, so KR is CCS over CAS PB. And KD, this is PC CS all over CCS. Okay, so just substitute that here. So K star. Okay, so K, not star, but K prime. Okay, so this one, so they're all bulk concentrations. So we have PC all over PA, PB. So this is equal to PC PA, PB. Okay, so KPA is CAS, PA, CS. KR is CCS, CAS, PB. And KD is PC, CS, CCS. Okay, and then the surface concentrations will cancel out. CAS will cancel out with this. CCS will cancel out with this. And CS cancel out with this. Okay, so you'll be left with PC, PA, PB, which is exactly this one. Okay, which is our overall equilibrium constant. So this is true. Okay, but we know that 1 over KPC is equal to KD. So I can replace this with 1 over KPC. So we have KPA, KR. This is divided by KPC. Okay, so going back here, so this bunch of constants. Okay, so that's actually KPC, KR, KPA. Okay, but here, okay, comparing this with this, you can see that this is just equal to 1 all over the overall equilibrium constant, K prime. So now we can write our overall rate, RA, as, okay, so we have K, FR, CT, KPA, okay, so times this, PA, PB, minus, we have PC there, and we have 1 over K prime. So this is K prime, and we have our denominator. This is 1 plus KPA, PA, plus KPC, PC. Okay, so this is our rate expression for the Ellie-Rideal mechanism. So this is our kinetic term, driving force term, and adsorption term. This is the rate expression that we just derived for the Ellie-Rideal mechanism. Here is an example that you can practice on. I would like you to develop a rate expression for the dimerization of isobutylene, IB. So this reaction follows the Ellie-Rideal mechanism with the following three elementary steps. So you have the adsorption of IB to form IBS, and then surface reaction, so Ellie-Rideal, so your adsorbed IB reacts with an isobutylene molecule in the gas phase to form your adsorbed product, diisobutylene, okay, so IB2. And then the last step is the desorption of the product. Okay, so isobutylene, and then you free up an active site. So you can assume that the product is weakly adsorbed. You can pause the video now. Did you get the correct answer? We can use the rate expression that we derived from the previous slide with A is equal to IB, B is equal to IB, and C equal to IB2. Then we can neglect the terms involving KPIB2, PIB2, due to the product IB2 being weakly adsorbed. So the rate expression will be this. Now I have a problem that I would like you to work on at home. Derive the dual site Langmuir-Hinshelwood expression, but for a reversible surface reaction. So the adsorbed species are the same as before. A and AB adsorbed on S, whereas B adsorbs on S star. The only difference is that the product AB can split into A and B in the reverse step of your surface reaction step. When you have done this, sketch the shape of the curve of the initial rate of reaction versus partial pressure of A for both the dual site mechanism and the Ellie-Rideal mechanism. And then take a picture of your rate expression and sketches and post them on our Padlet board. To summarize what we covered in this video lecture and the last one, we first discussed the steps involved in a catalytic process and established that the slowest step is the one that determines the overall rate of reaction. When internal and external diffusion are fast, the overall catalytic reaction involves just three steps: adsorption of reactants on the catalyst active sites, surface reaction, and desorption of products. A number of kinetic mechanisms have been proposed, but the most common are the Langmuir-Hinshelwood and Ellie-Rideal mechanisms. The former assumes two reactants need to be adsorbed, whereas the latter assumes a direct reaction between one adsorbed molecule and a gas molecule. The Langmuir-Hinshelwood mechanism assumes a second-order surface reaction between two chemisorbed species is the rate-limiting step. We derived the following form, which has a kinetic term, a driving force term, and an adsorption or inhibition term. You can use the method that you learned from this lecture to derive the rate expressions for other processes with different rate-limiting step and mechanisms. In the next lecture, we will start to consider the effect of mass transfer, specifically diffusion in porous catalyst, And we will model a catalytic pellet by setting up a material balance. We will then derive the Tila modulus and the effectiveness factor. And then eventually, we will design our catalytic reactor. And we will start with designing a fixed bed reactor.